So, what is a quark? In this video, you will soon find out. In 1964, two physicists, Murray Gell-Mann and George Zweig, were working on an independent theory for strong interaction symmetry in particle physics. They proposed that strongly interacting particles, known as hard-ons, could be explained if they were made up of fundamental particles. This led to what are now known as quarks, fundamental meaning that they cannot be further broken down and that they have no substructure. During their independent study, they soon realized that in order for calculations to work, quarks had to have a fractional charge, which is a very novel idea at the time. They proposed these values to be positive 2/3 and negative 1/3. In 1968, they began conducting several electron-proton scattering experiments at the Stanford Linear Accelerator Center in California. This was the first evidence that nucleons had an inner structure. They observed how the electrons bounced off, and this, along with other experiments, proved that these charges were valid. In similar particle accelerators, the particles are accelerated to nearly the speed of light. In a particle accelerator, scientists begin with normal hydrogen atoms, but then high-voltage electricity is used in order to force them to travel around in opposite directions along a very long path. With each pass in the accelerator, their speed, and therefore their energy, increased until nearly the speed of light. However, once these particles collided head-on, the collision showed evidence through the energy in order to conclude that quarks exist, and in fact they come in 6 different species. These species are known as flavors. Up quark and the down quark were the first quarks to be discovered, followed shortly after by other quarks. They found that these two quarks differed in their mass, charge, spin, and color, but it wasn't until over a decade later that the rest of the quarks were discovered. Protons and neutrons are made of 3 valence quarks. For protons, these valence quarks sum to positive 1. For neutrons, these valence quarks sum to 0. These values are consistent with the proton and neutron's known charge respectively. However, in these nucleons could also exist other types of quarks as well. The 6 quark flavors are up, down, strange, charm, top, and bottom. It is also important to know that each quark has its own respective anti-quark. For example, there's an up quark, but then there's also an anti-up quark. It's important to note that the up, charm, and top quarks all have a positive 2/3 charge, and the down, strange, and bottom quarks all have a negative 1/3 charge. Up and down quarks are stable quarks, but all anti-quarks are unstable. Quarks all coincide with the positive 1 charge of a proton and the 0 charge of a neutron. This is because a proton is made up of 2 up quarks and 1 down quark. Adding these quarks as known values of positive 2/3 plus positive 2/3 plus negative 1/3, you get the positive 1 charge of a proton. Similarly, a neutron's charge is the sum of its quark values, which is 1 up quark and 2 down quarks. This new information, you must be wondering how exactly these quarks are held together within a nucleon. Well, quarks are held together by what are known as gluons, which have a very strong attractive force. Inside of a proton, there are millions of quarks and gluons that are constantly colliding with each other, forming and destroying new ones. A gluon can be considered to be the fundamental exchange particle underlying the strong interaction between protons and neutrons within a nucleus. at all confused by my stating that there is constant formation and destruction of quarks and gluons within a nucleon, don't worry, because this doesn't violate any sort of conservation law. This doesn't violate any laws because quarks can appear and disappear when taking into account how energy can be turned into mass. Einstein's equation E equals mc squared states that mass can be turned into energy just as energy can be turned into mass. Because of the fact that quarks only make up a negligible amount of the total mass of a proton, all we need to conserve is the total mass energy of a proton. This is accomplished because of the amount of energy in the collisions within the gluon field of a proton. Therefore, no law is really ever violated. However, it is important to note that there are a few constraints to these rules. For example, the total number of up quarks must be 2 more than the anti-up quarks, and there must be 1 more down quark than anti-down quarks. So valence quarks add up to the total number of 3 quarks. Quark and anti-quarks of all other quarks must cancel each other out. Spin, colorlessness, and charge must balance each other out. For example, if there is positive 1, there must be a negative 1. The 3 valence quarks include red, green, and blue. This is because when mixing these, you get white light, or colorless, which is why protons are colorless. If you're at all wondering where all of this comes from, such as where they get their names from, then you'll soon find out, because quarks are up and down based on components of best spin. Strange quarks are given their name because they were observed in particle decays that had slightly longer lifetimes than they really should have had. Charm quarks were given its name because of how it fascinated the physicists at the time. It was almost charming. Top and bottom quarks were given their names by Harari because they were logical counterparts of up and down quarks. The existence of all of these quarks come from particle accelerators that were very similar to the Stanford linear accelerator mentioned earlier. The name quark was actually taken by Murray Gell-Mann and George Zweig, who were the founders of quarks, from a book by James Joyce titled Finnegan's Wake. There's a line in the book that states, 3 quarks for Master Mark. And Gell-Mann actually received a Nobel Peace Prize for his work in classifying elementary particles in 1969. Maybe by now you've noticed that I've only been talking about protons and neutrons, and I haven't at all been talking about electrons. So let me begin by stating that the Standard Model predicts many elementary particles, including quarks and leptons. Leptons are what make up electrons. Leptons are similar subatomic particles, but vary from quarks in that quarks make up protons and neutrons in a nucleus, whereas leptons include electrons and neutrons. The difference between quarks and leptons is that quarks interact with a strong nuclear force, whereas leptons do not.